Hi everyone, my name is Zachary Garrett, and today we're going to be going over some college level mathematics. This is the program that I use to pass my intermediate and college algebra courses. In college, as you can see, I received a 92.75 in this course. So what we're going to do is we're going to go over a few lessons in the intermediate algebra, which is normally what someone would take when they are just entering college had they not taken a course like pre-calculus or something like that in high school. So we can go to learn. This lesson is about prime numbers, exponents, and the least common multiple. So what we need to learn here, what we need to take away from this is there are a few different sets of numbers. There's natural numbers and whole numbers. So the set of natural numbers can be designated as n equals curly braces, and then those are the counting numbers, so 1, 2, 3, 4, 5, 6, 7, etc. Whole numbers are designated by a w equals curly braces, 0, 1, 2, 3, 4, 5, 6, etc. The three dots are called ellipses and are used to indicate that a pattern continues without an end. You can see the ellipses here. These are the curly braces here. So when it comes to the explanation of factors and products, we have factors as being 15 times 3 equals 45, 45 being the product. So the factors are just two numbers that are multiplied together to get a product. Another example of that is 7 times 8 equals 56. Again, 7 times 8 are the factors, 56 is the product. In the list above, 7, 19, 41 have exactly two different factors, 1 and the number itself. Such numbers are called prime numbers. The other numbers in the list, 44, 6, and 86, are called composite numbers. Note that 0 and 1 are neither prime nor composite. Another example of a prime number is 3. 31 is also a prime number because they're only divisible by 1 and their self. Prime numbers less than 50 are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. Continuing with this, the procedure to find the prime factorization of a composite number. So step 1, find the composite number into any two factors. 2, factor each factor that is not prime into two more factors. 3, continue this process until all factors are prime. The prime factorization is the product of all prime factors. Okay, so what I'm going to do now is give you an example of what prime factorization one example of what prime factorization can look like. I apologize if I can not make this full screen, but that should be good enough here. So we have the number 45. We can start with 5 and go 5, 10, 15, 20, 25, 30, 35, 40, 45. So that's going to be 5 times 8. And then the 8 can be further broken down into 2 times 4, and then further broken down into 2 times 2. That is the prime factorization of 45. continuing with this lesson. Find the prime factorization of each number. So we have 75 and we have 294. So the solutions to these examples are 75 equals 3 times 25. 3 is prime, 25 is not, which means that we can continue breaking the 25 down. And once again, all we need to do is write 25. We can go 5 times 5 equals 25. Then we have the 3 in there again. So now we can do 3 times 5 times 5, or we can write that as 3 times 5 squared. There are multiple different ways to write it, but those are the two most common ways to write it. Exponents. A whole number exponent is a number used to indicate repeated multiplication of a number within itself. An exponent is written to the right and slightly above the number. The number being multiplied by itself is called the base of the exponent. Note, the properties of exponents will be discussed in detail in a later section. So as the one application says, 3 times 3 times 3 times 3 equals 3 to the 4th. Now sometimes I like to write parentheses around it. If you type it into the calculator, it should still give you the same answer, whether or not there's parentheses around it. So parentheses 5. Bring up the exponent 2 equals 25. And you can just do 5. Bring up the exponent 2 equals 25 as well. But some math professors will think about that differently. In general, for any counting number and any real number a, we're going to have n factors of a, so just whatever number of a's we have. So an example would be a times a times a times a. These are the nth factors, 2, 3, 4 of a. That's going to equal a to a 4th because there's 4 a's here. 1, 2, 3, and 4. And of course anything that is written to the exponent of 1, so for example a to the first, it's going to be a to the first equals a. So 1 to the of 1 equals 2, just like 2 to the exponent of 1 equals 2. Whereas 2 to the second equals 4. Can also be read as 5 squared, or 5 exponentiated to 2, 5 to the power of 2. These are all examples of ways to describe multiplication. Least common multiples. The multiple of a number which are the products of that number with the counting numbers. Thus, the first multiple of any number is the number itself. All other multiples are larger than that number. For example, the multiples of 8 are 8, 16, 24, 32. So the multiples of a number, as described here, that would just be the multiplication of 8. So times 1 equals 8, times 2 equals 16. 8 times 1 equals 8, 8 times 2 equals 16. Find the prime procedure to find the least common multiple of a set of counting numbers. So what we want to do is we want to find the prime factorization of each number. List the prime factors that appear in any one of the prime factorizations. Find the product of those primes using each prime the greatest number of times it appears in any one of the prime factorizations. So for the prime factorization of 27, that can be written as 27, and we got 3 times 3. This is called the tree method of prime factorization. So 3 times 3 is going to be 9, so we can't use that. But if we write 27 is the same thing as 3 to the third power. We can also do 9 to the third power. 9 to the third power is 27. Not 3 to the third. 3 to the third is 9. 27 is 3 times 3 times 3. Prime factors present are 2, 3, and 5. So it wants us to find the least common multiple of all of these numbers. So what we have to do is we have to prime factorize all of these numbers. So 27, we got 9, 3. We can do 3 times 3. And we have 30. It would be 10 times 3, 5 times 2, 50. It's going to be 2, it's going to be 5 times 10, and 5 times 2 equals 10. And then what we want to do is 2 appears in each one of these trees one time. So we're going to take that 2, we're going to write it over here. Sorry about that. And now we're going to go to the next number, which is 3. There are 3 3s in this tree right here. So we're going to write 3 to the third power. All we're doing is taking the greatest sum that any of these numbers appears within the tree and multiplying it to find the least common multiple of these 3 numbers. 5 appears a maximum of 2 times. So do times 5 squared. So now we have 2 times 3 to the third times 5 to the second. So that is the same thing as writing 2 times 3 times 3 times 3 times 5 times 5. Or we can write that as 2 times, no, that does not work actually. So these 2 are equivalent. So now all we do is multiply those numbers together. Here we have the calculator. Sorry, I'm just trying to bring the OBD up here so I can show myself multiplying these together. 2 times 3 to the third. We want to move that over so we're not multiplying the exponent. Times 5 exponent 2. Then we get our number as being 1,350 or 1350. That is the smallest number that is divisible by 27, 30, and 50. Okay, that is the end of this lesson. In the next video, I will have some practice problems for you guys to try. Thank you.